Welcome. In this video, I'm going to go over the solutions to the SL Chemistry 2017 May exam for paper 3. I will be going through section A as well as the questions for option D, medicinal chemistry. In section A, they give you some information at the top and they tell you titration was done, but instead of having the volume of HCl and the pH, you have the volume of HCl added and the temperature. So the first question is calculate the percentage uncertainty of the volume of the aqueous sodium hydroxide. And up above, it's very clear that you've got plus or minus 0.5 centimeters cubed for a measurement of 25.0 centimeters cubed. And if I take that times 100%, I come up with a percent error of 2%. B suggests how the precision of this measurement could be improved. Well, when you look at the volume of the HCl, that was measured with the burette, and its error was only plus or minus 0.1. So using that burette would certainly improve the precision. And there may be other instruments you thought of, like a pipette or something else, but the pipette used for the HCl would be the easiest piece of equipment to use. Number 2, deduce why more heat was produced in mixture B than in mixture A. I think this is a little confusing because it sounds like it's a different mixture, and technically it is because you've added more HCl to it, but it's the same reaction vessel. So the idea that there's more heat released at point B than at point A means more HCl has neutralized more NaOH, which is an exothermic reaction. And then deduce why the temperature is higher in mixture C than in mixture D. And again, I think of it more at time C and time D, so that I realize it's the same reaction vessel. But what I see on the graph is that the temperature is starting to drop, so that indicates to me the end point has passed. And that means heat loss to surroundings is greater than any heat being generated. And then 3 suggests how the endpoint of titration might be estimated from the graph. I would look at the volume of HCl used at the point of the highest temperature. Question 4, state and explain how the graph would differ if 1 mole of sulfuric acid had been used instead of 1 mole of hydrochloric acid. Well, the amount of NaOH is going to be the same. So delta T, the overall temperature change, would be the same. Same maximum temperature should be reached, but the volume of acid used would be half as much. And that's because there's 2 H plus per H2SO4 versus just 1 H plus per HCl molecule. Number 5, the graph of temperature against the titer can be used to calculate the concentration of alkali without knowing the concentration of the hydrochloric acid using the enthalpy of neutralization. Explain how the concentration may be calculated in this way. So if I look up delta H, so I'm going to need to find that heat of neutralization for NaOH and HCl. And then I'm going to plug in, I'm going to calculate delta H for my solution that I'm working with by taking the mass of that solution and a C value for that solution and delta T. And this is what my graph is going to provide me with, is the temperature change. And as far as the mass and the C value, I can use those for water because that's commonly done with solutions. And once I have this delta H, I can divide the delta H of my reaction, or my solution, I guess I called it, by the delta H of neutralization. So this would be in kilojoules. This would be in kilojoules per mole. And by dividing those, that should tell me the moles of base used. And then B says heat losses would make this method less accurate than the pH probe. Outline why the thermometric method would always give a lower, not a higher concentration. Well, heat loss is going to result in, heat loss will mean a smaller delta T. So in MCAT, the formula we're using will give us a lower delta H, or a lower heat value. So the moles of base is always going to be skewed lower because of this. Suggest how heat loss could be reduced. You could use an insulated cup, would be the easiest one. Do your titration into a styrofoam cup instead of into a beaker. And D, state one other assumption that is usually made in the calculation of the heat produced. I'm not sure what they mean by one other assumption, maybe other than heat loss, I guess. But that density, as well as the C value of the solution, is the same as water. And part E suggests why scientists often make assumptions that do not correspond to reality, because it's all about if we're consistently using the same comparison, the consistency will give us relative results. We'll be able to compare the results to one another. So as long as I'm applying the same assumption consistently, even though my results might not be, spot on as far as accuracy, they're still going to be accurate relative to one another. And then F, outline why the thermochemical method would not be appropriate for 0.001 molar hydrochloric acid and NaOH of a similar concentration. With that weak a concentration, the rate of generating heat, the rate that heat's produced, would likely be less than the rate of heat loss, which means your results are not going to be anything you can use at all. And then at this point, you would have 4 options to choose from, A, B, C, and D. And I'm going to go through option D since that's the option we studied in my classes. So option D, medicinal chemistry. First question gives you this graph. You see it's therapeutic dose and toxic dose, and they're referring to A here, which you can refer to as the therapeutic index or the therapeutic window. But the significance is the larger A is, means it's a safer drug. You've got more room for error between having an effective dose and having a dose that's going to have harmful effects. Part B, morphine and codeine are strong analgesics. Their structures are given in section 37. Suggest the type of reaction used to convert morphine to codeine. And what you should notice is that the OH group gets taken off, and instead you get becomes an OCH3 group, or what's called a methyl ether. So it's sometimes called methylation. Just like hydrogenation or hydration, we're adding a methyl group in place of that H group. So methylation would be the proper name for it. Substitution, that may be enough. I'm not sure how they're marking this. But that is what's going on, is a substitution of a methyl group for a hydrogen group on that oxygen. Part 2, state and explain the action of opiates as painkillers. So this is worth 2 marks, and I think the main 2 things they want to hear from you is, first of all, they cross the blood-brain barrier. And that's because they're not as polar as some other medications. And then they also bind with what are known as the opioid receptors. And these two things allow narcotics to alter our perception of pain. So again, that ability to cross the blood-brain barrier and then bind with the opioid receptors is what allows narcotics to work or alter our perception. Number 19, solubility plays an important role in the bioavailability of drugs in the body. Suggest why aspirin is slightly soluble, refer to section 37. So when you look at the structure of aspirin, you should notice that there's a carboxyl and an ester group on it, or side chain, which gives it polarity. But those are just side chains, so the main part of the aspirin is still nonpolar. But it does have some polarity. And then it says, formulate an equation of the conversion of aspirin to a more water-soluble derivative. This is kind of an obscure question, but it's one that if they'd told you, if they'd suggested it's going to react with NaOH, you might be able to get it. So I've got my carboxyl group here, and I've got my ester group here. And when this reacts with NaOH, it's basically a replacement reaction where the hydrogen up here is going to get replaced by the Na here. So I'm going to end up with H2O. And then my more soluble version of aspirin is going to be, I'm going to have my rest of my carboxyl group, and the oxygen is going to become a negative ion with the sodium positive ion next to it, and then my ester group is going to remain unchanged. And even though a hydrogen bond makes things fairly soluble in water, an ionic bond, or these ions here, will make it even more soluble in water. Part C, a student prepares aspirin from salicylic acid, extracts it, and here's his results. The melting point is lower, and it's not nearly as sharp as the known melting point for aspirin. So suggest why the melting point of the student's sample is lower and not sharp. Both things indicate impurities. Impurities will influence the melting point, the temp at which aspirin melts, and it will also influence how sharp the melting point is. Part D, organic molecules can be characterized using infrared. Compare and contrast the infrared peaks above 1500 in pure samples of aspirin and salicylic acid using section 26 of the data booklet. So one similarity you should have found is that they both have peaks in the 2500 to 3000 range. And those peaks indicate an OH from a carboxylic acid, or from a carboxyl group. And that's true for both of them, that they had the carboxyl group up here. A difference you would note then is the other side chain here, a substitution. You would see with salicylic acid, there would be a peak at 32 to 3600. For the hydroxyl found in an alcohol. Or you could have said for the aspirin, you would expect to find a peak at 1700 to 1750 for the CO double bond in an ester. So you're looking for the peaks here. This peak of 2,500 to 3,000 would show up on both, whereas this OH group would be around 32 to 3,600 and on the salicylic acid only, and this carboxyl group would show up, or this ester group would show up at 1,700 to 1,750 on the aspirin only. Part E, the pharmaceutical industry is one of the largest producers of waste solvents. State a green solution to the problem of organic solvent waste. It's basically the idea of reduce, reuse, recycle. So a couple of them that the book mentioned were use safer solvents, safer for the health of the workers, safer as far as being non-harmful to the environment, safer as far as the process being used. And the other big one mentioned was avoid the use of auxiliaries. So simplify the process any place you can. I think either one of those would be fine for a mark. Number 20, the buffer formed by CO2 and hydrogen carbonate plays an important role in maintaining the pH of blood. So you want you to calculate the pH of the buffer. And if you look in the booklet, they give you the equation that the pH equals the pKa plus the log of your concentration of A minus over HA. So the values are all here. You just have to plug and chug with this. So that means I'm looking at 6.34 plus the log of 1.4 times 10 to the minus second over 1.25 times 10 to the minus third. And even though we didn't spend much time on this in class, this really wasn't a difficult one to plug into and get a pH of 7.39. Explain the effect of a large amount of aspirin on the pH of blood. It will decrease the pH because aspirin is a weak acid. Contains carboxylic acid, and if you have enough of it, it could certainly decrease your pH. And then number 21, antiviral drugs are designed to take different approaches to fighting viruses. Outline how Tamiflu works. So hopefully you remembered that there's two big enzymes, the N enzyme and the H enzyme. And right now, the antivirals we have tend to work with the N enzyme. So Tamiflu works with, it binds with the N enzyme. I think IB would probably take that if you didn't know that the actual name of the N enzyme is something called neuroamidase. So it binds with the N enzyme, which prevents cleavage, or in other words, the release of new virus particles. And that's really what they're looking at with the H and N enzymes, is either to prevent the virus from getting in or prevent it from getting out. The other option is to not let it reproduce if it gets in. And then B, they talk about it, that it's prepared from shikimic acid, outline how Greek chemistry was used to develop the precursor to overcome a shortage of the drug. They needed an alternate source. So an alternate source had to be developed or found, and there were three potential alternate sources. So alternate sources for shikimate included fermentation of genetically engineered bacteria, they were able to obtain it from pine needles. So So harvesting from pine needles was a second option. And the third alternative they came up with was extracting it from the Indian gum tree, or sweet gum tree, I guess. Indian sweet gum. And then C, suggest why the administration of antibiotics to humans and animals can affect the environment. This is just one mark, so I think you could address either one, but humans dispose of it incorrectly. Humans dispose of it in the trash or down the toilet. It can end up in our soil and water. So if humans dispose of it inappropriately, that's an issue. And animal waste presents the same issue. In either case, the antibiotic ends up in water sources and soil.